Good day. Good afternoon. December 26, 2023. As from a desk of Ross Finlayson, some more about moment and motion. These complementary concepts which help define a divide, a dichotomy, which together still arrive as one. Moment and motion. The most usual familiar fundamental principle from ancient times of that which is the explanation of things is that which goes up must come down. The rise and the fall. What goes up must come down. And this was according to the usual, most familiar and available experimental setting called our terrestrial setting, where gravity is always available as a constant in large part for such matters as arriving as why things go aloft and as why they descend. So this kind of combines both of these kinds of notions of the restitution and oscillation and attenuation and dissipation. While at the same time in our deconstructed of elementary accounts, we can have those both separately, vis-a-vis our systems, our models, our theories of how the things are and why it's arrived at that the ancient traditional principle of what goes up must come down is the same theory today as what we call the second law of thermodynamics and entropy. The entropy always increases. So in the one sense, it's as we're arriving back to zero, an equilibrium. In the other sense, it's always attaining to zero, an equilibrium. We have this kind of opposite concept. It's also called entropy, where when you study and learn these things, that there's lots what goes into whether something is organizing. Whether it's got a tendency to so reach these equilibria, or a propensity to achieve a higher form. So these complementary concepts and notions and duality of attenuation and dissipation for oscillation and restitution make for these tendencies and propensities that overall that pretty well helps to provide a scale for the balance of the things. So today the principle is called least action. Least action is the idea that there is no free work. There is no perpetual motion machine which will always achieve an ongoing with providing an output without otherwise being an open system and having an input. This is also related to what we call the balance of symmetries and conservation laws about continuity laws. So these frame pretty much all such manners of our thought experiments and our attachments of these models, mathematical mental models, to the physical models, relating them to systems of units, and with regards to the measurable of the observables of science, and then with regards to that making for what can be seen as an approach when the notion of those principles are simple and fundamental enough, yet they still provide the grounds of the reasoning of all these other notions like motion and rest. Now for motion and rest, everybody's familiar with Newton's laws. Motion stays in motion, rest stays at rest. And then the more ancient rules, we're trying to figure out stuff like when does the application of an input slide the block up the ramp? And as with regards to that, the tendency then was that things would come to a stop. That generally there's the notion that as energy is input, then it can provide a linear impulse. And then when it stops, then it attenuates and dissipates and falls away. So how that's related usually today in terms of what's in motion stays in motion, what's at rest stays at rest is friction. So friction is the idea of that there's the forces and couplings of stresses and strains vis-a-vis the static and dynamic that friction has. First you have like starting friction or static friction to overcome a tendency of something to remain at rest vis-a-vis its interface and its surfaces. To dynamic friction is how to keep it sliding once it's not at the rest that it was, the equilibrium of its stasis, its static state. So in this sense, there are, besides of our fundamentals that help us make abstract the formulaic approaches to the classical and linear impulses of all these sorts of things, that there's well arrived at how there are the things that relate to the classical when they were still dealing with things always in the mesoscale, always in the terrestrial, always in the real, and with regards to observables and the theories of, and so far that they could reflect that in what was the measure and the quantification of things. Mentioning quantities and the quantification of things gets into two separate concepts that at the same time relate the same to each other. One is the quantization and quantification of something that is vis-a-vis the qualities of something, the quantities of something, a measurable amount of something related to a system of units. The other notion is from logic that quantification is as of the comprehension of a variable in its terms. And so the realization that over a space of variables range, that it has a certain domain of what is its value, that we have quantification is one thing low in the theory, symbolically and logically in theory, another thing omnipresent in the theory, or very, very much usual in all the surrounds, quantification. So with that said, then there's just kind of carrying forward in this development of the idea of the theory of the symbols and the relations and the concepts of modeling the theories and relating them to everybody else's theories, and specifically to this one called sciences theories, writ large, is that then it's a great sort of exercise to have these things available to then explain both what we have as the fundamental and then how that relates to the practical. And then as for the practical, how that's arrived at from the empirical. So we have the theoretical and the empirical, vis-a-vis the theoretical is our ideals and they're perfect, and the empirical is the ideals of what can be discovered in the empirical realm, empirical in the system of units and these kinds of things, and as how they come together. There's, for example, a study of what's called tribology, and this is the idea that all these things that are nonlinear with regards to their results or emergent phenomenon sometimes included in terms of the engineering and the statics and dynamics that, well, our classical accounts really kind of let out and aren't necessarily apropos, or they don't give the right numbers. That then there's still this kind of all what's they call the apocryphal sometimes, that which is known but isn't really the exoteric of the theory or kind of how it's relayed vis-a-vis what need be received in terms of the empirical and the theoretical. One is fundamental and the other is practical, in the usual sense that in a perfect theory, they're the same. So it results that they're sort of the same, and the whole notion of the ubiquitous success of mathematical physics and science is that over time, it's more and more arrived at from the theory and available formally in this manner vis-a-vis what's arrived at from trial and error, the reproducibility of experiments vis-a-vis the falsifiability of experiments according to a theory, soundness, validity, all these other usual notions of scientific method after the statistical method after the phenomenal vis-a-vis our noumenal, which enlightens our mind and allows us together to comprehend as fully as they exist, these concepts, without needing much attachment or a mental catalog or the mental discipline of too many things at once. This is why theory and fundamentals in the theory are so relevant to anybody who wants to carry the most weight with the least baggage. So, today then, what I did is I found some more books, and so I'll just kind of ingest them as a sort of way to help reflect it as part of the body of knowledge, that they have their some sense of an inspirational value or something to relay. So let's take a look at this. This first book, well, this is just a catalog from a bookseller, and I got it in an antiquarian book fair, and it's a bunch of books, antiquarian and rare books, and it doesn't really have so much on the science, but it's got a bunch of stuff about music and screenplays. Mentions Adorno, Ex Libris. To opine on a historical figure's personal relationships is fraught with factual and moral problems. Well, we kind of lionize our heroes, and we have apologetics in the sense that for our ethics and morals, we kind of hold up what's good, and at the same time have our own free realm of thought, which is a great thing. Means the Royal Economic Society. So this is just an example of in the stacks and all over recorded history, that largely the canon we receive is textual, and in a sense related as graphical. And then as far as the ability of a mind to input and output information, it's textual. Here in words, you know. It's a book on gas turbine engineering. It's an industry publication, and it affects and reflects a lot of what is the empirical that doesn't necessarily have it so easily arrived at from the theoretical with regards to its own fields, and it has its own empirical milieu of what these things. So when we say empirical, we don't necessarily mean with regards to the imperial, that with regards to the empirical, that is regard to systems of units, and particularly how sometimes besides our standard units and their independence from otherwise what are running constants and these things from our theoretical, so that our theory is all formal and well-defined and stands up for itself and straight and is related out to its pieces, that the empirical helps reflect things like what is a gallon, what is a ton, vis-a-vis mass and weight, what is a dram or something like that, vis-a-vis the size of a kidney and an ounce of water by its weight or its volume, given temperature and this and that. All these kinds of things are kind of what's called empirical, and all such matters of standard measures of things are kind of so related as to why it is like so, as to like why is a 35-pound box or a 70-pound box like so, because these are limits then that over aggregates and areas that in terms of moments in motion, the measures arrive at tractable things that they can go together. So the author describes things like different, the viscosity, the properties of materials that all together have to form a system. So a system as a closed system is well understood as being circuitous. And a system that is an open system is well understood as being the throughput of the system. And then what's the open and closed is as of the dynamics of this system, as what respects outside the system, that it's a unit of a functional apparatus, and inside the system, it's a unit of a functional apparatus. These kinds of things. We talk about uptime and downtime, mean time between failures, mean time between replacement. These are usual statistics in an industrial setting that help people in their operations research understand how to design factories and plants and have them operate economically over extended durations. The single-shafted twin-spool engines calculated above could well be practical turbojet engines. They will be used as a basis for comparison with a number of variations to the cycle, but before that, one level of simplification will be introduced. So here we get into the ideas of the practical simplifications of things with regards to mode A and mode B, and success modes and failure modes, or error modes, these kinds of things. With regards to the duty cycle, which is the expected operation of things over time. What's in sometimes in computer engineering we call that availability, vis-a-vis traffic and performance in something like the enterprise core system of an information system. The main parameters. When the Soviets designed rocket engines in the space race, what they did is, first of all, they had a bunch of scientists whose dedication was provided to it. And secondly, what they had a lot of was trial and error to establish what's going on in the parabolic and the reflection and the cones and such like that. And then with regards to the introduction of gratings or otherwise in the blast chamber and these kinds of things, what goes on with regards to making the detonation of rocket fuel into a linear impulse from just a highly chaotic dynamic environment in its impulse, where it results what's called specific impulse sometimes, or capacity to do. A pioneering combination of the gas turbine with steam was the Brown Bavaria Velox boiler of the 1930s. The combustion chamber of the engine is the flame tube of the boiler, which by virtue of the high gas pressure is considerably more compact than a boiler having its combustion at atmospheric pressure. This made it suitable for rail and marine use as well as stationary use, but its efficiency could not match the use of exhaust heat for steam generation. A more powerful version uses the blast from the jet in addition to the heat for snow clearing from airfield taxiways and runways. Old turbojet engines are used for this. The high fuel consumption is offset by the time saving or even the ability to open the airfield at all on any given day. Well, with global warming, it's harder to find snow days. But given the bubbles that they move around bigger, when they show up, they're bigger. It's dynamics. So. Engines, turbines and engines. One of the most remarkable facets of the manufacture of the flying machines is that besides Bernoulli and the notion of lift is the gyroscopic effect of the rotating turbofan. It holds it up. Moment and motion. So this I picked up today, and this is kind of cool. It's an updated brief edition of George Bell's, Abell, George Abell's Exploration of the Universe. And so what it has is all kinds of a survey of the contents that are visible from the sky. And then it gets into various techniques to approach how to survey the sky. And it includes things like optical astronomy, radio astronomy, and then also, for example, the infrared, in terms of what's called the spectrum analysis. After what you get in terms of astronomy is that space is mostly empty, but it's full of cosmic dust. So in the cosmic bellows and the cosmic clockworks, as for models of stellar pulsation and the cosmic clockworks, as it were, then what is it found that over sufficiently large distances, there's just enough dust that only very specific frequencies are really available to be identified. So we call this the hydrogen line. And how it's figured out is that when you try to study something in the sky, you have a theory of stellar pulsation and stellar formation, and the catalog of ontology of stars. And then you figure from that when they have what would be standard candles, because you can't really measure something distant in the sky that doesn't move according to parallax and relative motion and Doppler. There's no other real way except a standard candle. So what the standard candle is the idea that some of these stars have the particularly well-known properties, or they're estimated so be. It's a theory that they so are. And then the idea is then for the optical astronomy and also the radio astronomy and variously that these spectrum lines allow us to figure out discretely what's expected to be visible and then how to help estimate distances from correlated items in the survey. So one thing that's really related to is the discovery of spectrum lines from elemental area analysis. And so if you've heard of a mass spectrometer before, what it does is it determines from the excitation of ions of molecules of material, it's able to extract from this continuous spectrum of these things, spectrum lines, which are particular indicators of various, is associated with various characteristics of the elements under consideration. So it's this similar and exact same sort of notion with regards to stuff like neon lamps, and then also with regards to the sodium lines and the hydrogen line, go a long ways to explain how it was possible to identify these things from the apparatus. Radio astronomy then is a secondary sort of consideration. Then we have, these days also we have the neutrino observatories and the gravitational wave observatories. So this book has got a lot of great pictures about Mars. Here's Mars, the Sun, Hale Observatory, star clouds and dark obscuring matter in the Milky Way in the region of Sagittarius. So we live in the Milky Way galaxy, and we live in that, and that is in the Laniakea supercluster. And that's the largely the edge of the visible universe. Man by nature is curious about his surroundings, particularly about unexplained phenomena. To satisfy his curiosity, he may employ one of two entirely dissimilar approaches. The first is to invent, to make up an explanation out of the imagination. It's called intuition. This procedure is extremely efficient and answers all the big questions. Here, of course, is the root of myth, superstition, and primitive religion, until you build a kind of enough information to have a scientific approach to these things. One such religion that grew rather naturally from a very early and invented idea of the nature of the universe is astrology. So you got astrology and fortune and these notions of the auguring events, prophecy, and astronomy, which is as of these are observations, they reflect a catalog of data, can interpret the data, it speaks for itself. So the purpose of science is to find order in the chaos of natural phenomena. So here the author goes to quite a good extent to help explain the theory that goes in this, that astronomers and big astronomy is considered where a lot of the great minds went into that with regards to the fact that it's so remote and that the sky survey is essentially, we only have an entirely passive view of what arises from it, that it's in that sense it's also that the most highly dynamical and absurd as the universe could create objects are as part of the sky survey and cosmology. So, this vis-a-vis experimental physics of the what would otherwise be non-observable, and then vis-a-vis the empirical, which anybody can whip out a meter stick and determine on their own. That the idea being that for science that it's falsifiable, reproducible, and observable, that these are observables for our passive and active, intromissive and extromissive senses that define after we have our phenomenological senses, and before we have our noumenal senses, the object sense of a word sense and a number sense. These being the general ideas that the concept of number and ideal forms, shapes, and proportions develops very early as usual abstraction. It's found in the mind. So it's considered that besides necessarily the physical senses, empirical, are also the noumenal senses, the object sense, word sense, and a number sense. So this is a great book if you would like to know a survey of astronomy. Mentions Galileo. Galileo's astronomical contributions. Sometimes in the 1590s, we were just talking about Galileo, so let's see what he says. Galileo adopted the Copernican hypothesis of the solar system. In Roman Catholic Italy, this was not a popular philosophy for the church authorities, It was primarily because of Galileo, The prevailing notion at the time was that the celestial bodies belonged to the realm of the heavens, where all is perfect, unchanging, and incorruptible. Perpetual circular motion being the perfect kind of motion was regarded as the natural state of affairs for these heavenly bodies. Once Galileo had established the principle of inertia, motion in motion, it was no longer necessary to ascribe any special status to the fact that the planets remain perpetually in orbit. And this is where the orbit is sort of the first-class trajectory. You got the orbifold and the trajectofold or on the manifold. So the orbit is kind of, whereas otherwise we just think of everything moves in a line, is that actually everything's always orbiting everything else. This is the idea. What does need to be explained is why the planets moved in curved paths around the sun rather than in straight lines. So here it's what's called a theory of rest exchange momentum for general theory of relativity first before special theory of relativity, and then it's classical inside the inverse square force gravity. It's because of a fall of gravity from the outside. So then it helps explain the drop off or cut off or fall off, what these days is called modified Newtonian dynamics. That the Earth and its ephemeris is pretty much mostly defined by what's called the Jet Propulsion Laboratory's parameterized post-Newtonian ephemeris, with regards to our modern premier theories called general relativity, and that being Newtonian and the limit, and that having inverse square law is the force of the field we all inhabit in the theory. In an analogous way, objects on the Earth would not be swept off and left behind if the Earth were moving, for they share the Earth's forward motion. Galileo's telescopes. So this is an example of a tool, a lever, to provide more observables. The first telescopes that attracted much notice were made by the Dutch spectacle maker Hans Lippershey in 1608. Galileo heard of the discovery in 1609, and without ever having seen an assembled telescope, he constructed one of his own with a 3-power magnification. The traditional, or the usual these days, camera is what's called a CCD. It's a device which interprets coordinate spectrum, the inputs, which have with regards to the luminance, and then red chrominance and blue chrominance, that it's a green screen, luminance, and with regards to then chrominance and chrominance, and the usual apparatus, what is on the extremism side called red, green, blue, chat up as primary colors to other colors of any sort. Regards to hue, saturation, and brightness, or hue and intensity, these being the ideas about how the modern CCD camera, which with its gigapixels, is just the result of a pretty simple apparatus that can be manufactured in the billions and billions and billions on a very, very precise and tiny scale. So before this was discovered, the telescope, it had been around for a long time. The concepts and the notions and all the stuff are very familiar. The ideas like the astrolabe is an idea of thousands of years. There was, before it was like discovered, there was this kind of thing. Or the Antikythera, it's a little crank computer, thousands of years before it was discovered, by some British man or something like that. So this is just getting to the idea that the whole apparatus thing is like, so here's a picture of Isaac Newton, and this is kind of what he looked like. Isaac Newton was quite diligent and varied in what he studied, and he really put a lot into it. And it's something to be said that he was able to bring together some of these greatest notions of science at the first time. Picture of Einstein. Einstein is cool. These are the schools of men or women, schools of people that we have as our touchstones of the collected results that arrive today and since then are disclosed. And so then we have that as the exoteric facing side, the public facing side of the theory. Usually the esoteric side, which are like the rituals or the secrets of the theory. And it gets in experiments like, well, if you throw a ball hard enough that it enters orbit, will it land? Can you catch it all the way around the world? They do that these days. How do those rockets stay balanced when they take off and land? Well, they have what's called MEMS, and so they use basically large banks of gyroscope arrays on a very small scale, all holding it up together. You just charge those up, and then it's like, stand it up. The Foucault pendulum. The pendulum and Foucault's measuring of the precession of the pendulum over the course of the passage of the rotation of the Earth also speaks to then for the experiment of Allais, Allais, Allais. So Foucault's pendulum and then Allais' pendulum are both really kind of critical experiments that established a lot of stuff that goes on with respect to relative motion and the frame, and then all such things which arrive later in the theory. So with regards to Foucault and Allais, I kind of describe them as similar going forward, because what Allais does is he says, let's set up a Foucault pendulum during an eclipse or syzygy when gravitational objects and large, our cosmological sky survey, come together. And he's like, well, notice it dips here. Eclipse. Foucault at the North Pole. Latitude and longitude of Washington, D.C. So here then he gets into a description and providing the nomenclature of the terms that identify the relations of the objects with regards to apogee and perigee, orbits, and the ephemeris, orbits, and then with regards to things like the sidereal days and this kind of stuff, orbits, and the revolutions of the stars, and their motions inside their frames, their closed systems, their open systems. In the wider frame, their open system and closed systems. Sidereal is kind of hard to figure out because it essentially is like the bit where it catches up going around the circle. It's like, well, isn't it just around the circle every time? It's like, well, yeah, but it adds up just a little bit left. And so then there's that, and with regards to something like the path integral, it's like the path integral is a particle and it's a wave. So when this particle moves, it travels as if it travels all the paths, the sum of the histories. So when you integrate the path integral, isn't it 1.000000000? Well, yeah, but then it's 1.000000181. This with respect to something like the doubling space and the halving space, angle doubling and doubling measures, which are in mathematics how we relate the continuous and the discrete. With regards to the discretization of thing, doubles some parts of it from perspective and projection. Then that we can have mathematical models of that. This is the non-standard. After Zeno and Allais, this is like, also this is all perfectly classical and standard. It's constant uniform motion in time. And this other stuff is with regards to the continuous and the discrete, and the individuation of elements of the continua as the quantum, and then also as with regards to the sum of potentials around a thing, the total. So, yep, with this way, with such a grab bag of terminology as this for the nomenclature of the things, it really helps to relate a lot of things together and explain both the elementary accounts and the deconstruction to like these are primary elements like energy and its quantities, of energy in the different forms and its quantities, and how these things change and stay the same, moment and motion. The dates of observance, the calendars. Astronomy, of course, is usual first timekeeper of regular periodicity and time, the day, the lunar cycle, solar cycle, various organizations of the constellations, the eclipse, the syzygies. Syzygy is when an eclipse is kind of like when one body comes in between two other bodies, and a syzygy is when they line up. Not exactly necessarily the same. If you've ever observed an eclipse, which is where the Earth passes between the sun and the moon, that's really great because you can observe the moon's face, and optically it's really remarkable how it rolls over the focus, and it does the thing. I mean, this is one reason why people find it so fascinating, the observance of these things from the sky survey, because they help explore these dynamics that would be present in otherwise the classical and mesoscale milieu, just too fine to observe, it's too sublime to observe. Radiation laws. So talking about the wave propagation and stuff like this, one's like, what does a wave make? It makes waves. It's radiation. It radiates energy. It's waves. The energy associated with the absorbed radiation heats the body and would continue to heat it indefinitely if the body did not begin to radiate that energy away. And here it gets to the notion of when we were talking before about the spectrum lines. And then it get talking about the blackbody radiation, which is something heats up so much that it starts to actually emit light. And then that's what science got into what's called the ultraviolet catastrophe, because it's like we have discrete things and we have continuous things, and we still need this mathematics of the doubling spaces and continuum mechanics to explain how all this works. And then it's like, well, we've got spectrum lines and we got the electron physics, so we can actually measure a quantum and say it's a given value. So after the ultraviolet catastrophe and Rayleigh genes, then you got electron physics and spectrum lines. Amazingly successful. That's what provided the theory, the building blocks, to make all kinds of these scientific things, vis-a-vis like the Soviets and their rocket nozzles, or let's invent vacuum tubes and try all kinds of combinations of the pentodes, diodes, anodes, cathodes, gates, phase arrays, contents, and put electricity in them and see what happens. The empirical, what resulted, stuff like the transistor, PNP transistor, NPN transistor, silicon die, etching on chip, digital electronics. So after the ultraviolet catastrophe, which is still being resolved today, then today where science is at is it's got its second catastrophe, which is about how does gravity fit in the middle of quantum mechanics and general theory of relativity. Well, it does. Max Planck is like, here's atomism. Here's about 5 orders smaller than that, and so here's stuff that'll start building the quantum statistics and everything that adds up for it. Atoms are the building blocks of matter. They are the smallest particles into which a chemical element can be subdivided and still retain its chemical identity. So the periodic table of elements, of course, is one of the greatest things of all time. And with regards to the notion that there's an order in the universe and the laws of physics are the same everywhere, and that there's a science of it, and as with regards to how it was discovered, and then when it was discovered, if it was Mendeleev, or excuse me if I don't really recall exactly what the idea was, but he put down a periodic table of elements and there were spaces in it, so they looked for elements from those spaces and they found new elements. One of the examples of when theory itself arrived at these things vis-a-vis, just the myriad properties of elements in nature. Energy level diagram for hydrogen. The atom is ionized. Atomic transitions. Atoms which absorb light. In the photosphere of the sun, 6,000 kelvins. Only about one atom of hydrogen in 100 million is excited to its second energy level by the process of collision. The Balmer lines of the hydrogen spectrum arise when atoms in the second energy level absorb light and rise to higher levels. At any given time, therefore, most atoms of hydrogen in the sun cannot take part in the production of the Balmer lines. They're left out because in the theory, it's like, one at a time, keep it in mind. "40-inch refracting telescopes." Well, carrying on here, this is something that helps establish a background of the field of astronomy. Brown twists is a particular thing it reflects like Hall effect or Coulomb force and Cherenkov or Bremsstrahlung. These are notions from the theory of like, wow, it's kind of we got this outside effect, Casimir effect, Coriolis. It's rest exchange momentum. It's light speed rest frame theory. Neutron stars. It follows with a great glossary and an index, I imagine, helping show for all these different terms a reasonably brief description of a definition. Some principles of the mathematics involved: algebra, geometry, arithmetic. Orbital data for the planets. It has the little symbols for each of the planets. As what was after astrology, then there was alchemy, and then today we have astronomy and chemistry. But it's really the roots of the same thing. Tables, an index, and a picture. The southern horizon, the night sky in January, night sky in February, night sky in March, April, May, the rest of their calendar year. So then we get back to waves and layered media, and see here owns the waves with regards to this book and this book here. And speaking of waves and particles and waves, from the quantum mechanics, so that was like the big side of science, the outside of science. And then the inside of science is this notion of the quantum mechanics and particle wave duality. And so by the time it came around to 1900, it was well established that light was a wave. Diffraction. This is, for example, here's an example of a diffracting crystal. This would have been the tool that Newton had, to just start to figure out the rays of the spectrum, and Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, this kind of stuff. So then this fellow right here, his name is David Bohm. And so there's this guy named de Broglie, and he's a Frenchman, and during the time of quantum mechanics, he was really instrumental in establishing that the wave collapse about the continuous wave and the discrete particle still is of this wavy nature. And with regards to then in Annus Mirabilis, it was firmly established for electron physics first. Electron physics stood up as like, we have a subatomic theory of matter. Now we have electrons is quantified with given fixed values. And so then the idea that came up out of quantum mechanics and indeterminacy with the diffraction and the Young's experiment and the camera obscura and the dual slit experiment that occluding one or the other or having both open made it so that the wave forms as if it takes all paths, the sum of all histories. So anyways, Bohm has his notions of implicate order that help arrive after that. The stochastic interpretation of Copenhagen was a very useful milieu, and kind of like not just the old quantum mechanics and not just this statistical interpretation for the statistical ensemble, which is how we define our field number formalisms for all such manner of unified field theory and quantum scattering and tunneling, or how science does it if you put the physics together. That then Bohm helped return to something that was abandoned. It was like, thusly, it's a statistical, we leave aside these other notions of how they come together. And he still held this notion. He's like, well, according to my theory, it's like this, so the other way. So now that's coming kind of back together and around. It's like, oh, well, we have to put it back together. Kind of like if you look at Einstein, and it's like, I got these great theories, and they work great, and they provide numbers for these discrete mechanics of these things. Then it's gotten to this creating. It's like, now I'm going to I introduced special relativity first, and then general relativity, and now I'm going to put the cart back before the horse, as it were, and general relativity is in front. Special relativity just lets out. Yeah? So Bohm and de Broglie make for a real wave function collapse. And so this is like for the particle wave duality. We have resonance theory above that. Now, I kind of, mentioned this before in some of these other talks, but it kind of results in kind of self-contained little science in so few words and so little time. What is the difference in the meaning of the word part and fragment? A part, as I said, whether mechanical or organic, is intrinsically related to a whole, but this is not so for a fragment. That kind of helps. It's also related pretty well to what's called axiomatic set theory, which is our usual foundation of theory, of descriptive set theory, which is kind of the usual foundation in theory for modern mathematics. For set theory, there's part theory, but then the set that's only regular, up to the class set distinction, is fragments. Yeah. This amuses me very thoroughly. It's the light bulb is on, if you get what I mean. So. Ondes. C. Coulson's Ondes. Printed and published in Great Britain by Oliver and Boyd Limited Publishers. All right, so what do you consider coordinates? So coordinates, we point at Descartes. And Descartes is a philosopher, and then he's known for at least three things, and one of them is coordinates, and another is his computations of the spectrum of the rainbow and his contributions to physics. And then another one is his theories on thinking and the relation of the teleological and the granting of the personal as free will, regardless of whether or not it's falsifiable that it is. Okay. So this is where I'd kind of bookmarked before as I was leaving off. And so what I was reading about was, you got Bessel equation, you got some of these numerical series and equations after sine and cosine, like Bessel, and here's D'Alembert by a method similar to D'Alembert's. So you got the linear fractional equation, you got Clairaut and D'Alembert. So these are some of these original developments that were general, specific, to get into the things, and they're descriptive. That here's where we began and reached yesterday. What I'm going to do is I'm just going to briefly skim over the table of contents. And so in this manner, we'll kind of get an idea of the overview of the scope of this kind of thing. Harmonic waves and plane waves, we just got into that a bit. The equation of wave motion, this was defined by principle of superposition. This is that waves sum to waves, or with regards to how waves collapse to waves, the inner and outer products of these things. That is kind of like the state of suspended being with regards to when it's evaluated and how it is. So it's what's superposed is as what's about the things. Then this theory of some potentials, it also results that the classical impulse is just potential in the central as well, which kind of makes a nice helping for a closure, even though it's entirely intractable what that superposition of things is. And all what we have as sensible and fungible and tractable, classically and directly, is so linearly, then this extra linear, the nonlinear, which just means superlinear, comes together to form a coherent thing. And these sorts of things become available to our object and number and word sense because we introduce these concepts of the infinite and infinitesimal, that they become real and manifest in our own minds. Then they become available as objects of this dialectic. And so that's a learned thing. Special types of solutions. So for a lot of these different cases, like I can't figure out anything, but I know for at least these three different kinds of ways, there's at least one of these three kinds of ways to figure it out. List of solutions. It's always good when you're looking for a solution to find one that's already found. This is the opposite of, though, if you want to go seeking to prove what you seek to prove and this kind of stuff. But they're about the same. The equation of telegraphy. So telegraphy kind of involves both the Doppler effect and the limit of the rate of something to travel and return. And then that's mostly modeled in like the wave tanks and the acoustic and the phenomena, vis-a-vis what we discussed a lot on the differential equations about orbits and the orbifold and the manifold and these kinds of things which come together and go apart, starting, stopping, meeting and parting. Rest exchange momentum. Pseudo-momentum as the real quantity underneath observed momentum classically, with inertia is conserved and pseudo-momentum is conserved openly. That's what I'm talking about. Special types of solutions. Equation of telegraphy. You got the transmission and then dissipation kind of associated with it, whether it's power lines or whether it's a signal. And we got to talk about amplifiers and expanding the signal. Exponential form of harmonic waves. So that might be something interesting to look at. So that's in chapter 1. So as there's 8 other chapters in this book, 7. There's 7 other chapters in this book. And what we can plan to look at later is some of these other things. But the exponential form of harmonic waves gets into the relations of numbers and various formulas and their forms, and forms that have infinite expressions, expansions, and those that have finite or closed forms, which are almost always usually more tractable. But that the infinite sequences offer the methods to get into make things tractable with when you can otherwise not even get beneath the surface. So most of the waves with which we shall be concerned in later chapters will be harmonic. They they have these superpositions that are well defined and that they fall back down. They're harmonic. This is partly because, as we've seen in section 8, harmonic functions arise very naturally when we try to solve the equation of wave motion. It is also due to the fact that by means of a Fourier analysis, here in the differential dynamics is discussed a breakdown of the Fourier style analysis. Any function may be split into harmonic components, and hence by the principle of superposition, any wave may be regarded as a resultant of a set of harmonic waves. This is kind of well known from Shannon and Nyquist and sampling and reconstruction theory also. Signal theory, information theory. When dealing with progressive waves of harmonic type, there is one simplification that is often useful and which is especially important in the electromagnetic theory of light waves. We have seen in Formula 11 that a progressive harmonic wave in one dimension can be represented by phi equals a cosine 2 pi kx minus nt, which will be familiar from where it was defined last time. If we allow for a phase epsilon, it will be written phi equals a cos this quantity 2 pi of the quantity kx minus nt, all that plus epsilon. Now this latter function may be regarded as the real part of the complex quantity a times e to the plus minus I of this quantity 2 pi kx minus nt plus e. So for this, you need to kind of know the Eulerian and the Gaussian notion of the complex analysis, and with regards to Euler's identity, and then with regards to how that makes for the real part of this exponential. What is so profound is a relation that then the arithmetic makes for addition formula about the exponential and its terms, about these methods and analysis. So it is most convenient for our subsequent work if we choose the minus sign and also absorb the phase epsilon and amplitude a into one complex number a, big A. We shall then write phi equals big A times e to the 2 pi I times quantity nt minus kx. A equals a times e to the negative I epsilon. So it's just the phase left over as a complex part of this thing that is like so. And it's entirely intractable. It's imaginary, and the detachment and the distance from the real component back to this kind of real component is unsettling or jarring or doesn't make sense. It doesn't have a connection. It doesn't have an attachment. We can't make a commitment. So at the same time, how that becomes sensible and fungible and tractable is to get back to knowing that the reason why we use these symbolic forms and they maintain their staid relations throughout all the rest of these things isn't according to just the properties that are employed. Like we said, we only pick out the phase. We only take off the real part. We put on blinders, in a sense, to these other notions of on or off the ridge and this kind of thing with regards to keeping it all together. So in that sense, it's possible to help, internalize. Otherwise, what in a vacuum of things is just entirely separate. That these are the kinds of things that help explain why then, when it gets in this formulaic form, you also got these other great properties of addition, arithmetic, or otherwise the number system, the operator calculus, and all the things fitting together that make that fungible and tractable. Well, all right, that's kind of what I hope to talk about today. It was moment in motion, geometry is motion. Let's see here. With regards to that, in the cosmic clockworks of a sense, that the open and closed systems in physics are profound, and it's kind of necessary to that the notion of entropy in its one way ultimate finality is its opposite, and the way things are, and any types of things that are the classical action in the moments of things. That then, with regards to the scientific method, and these are observation, reproducibility, experiment, and falsifiability, it's kind of helped declare this is a common thread. It's practical. It's derived over time from what was the practical, and also what was the surrounds, the sociological, and that which made it possible for these ideas to be disseminated and to be productive, for many people. That all these kinds of things come together to just help relay that this sort of, for me, I just taught myself a few lessons of these things, putting the words together, and that the very practice of relaying something is that if you really know something, it should be possible to relay it directly to anybody in so few words. That these are the kinds of things that help come together and make it a unified course, while that everybody has their own view, their own path and course, that there is one, and it's ours. Goodbye.